So when we last left off, we were discussing mass spectrometry. We talked a lot about carbon-carbon bond fragmentation. Next, we're going to talk about some common functional group fragmentations that you see with non-carbon atoms. So for example, alcohols often undergo alpha cleavage next to the carbon-alcohol bond to yield a stabilized cation. So as we see, a lot of these fragmentations are based on this idea that fragmentation of a bond yields a highly stabilized carbocation. Alcohols can also undergo dehydration to yield a carbon-carbon double bond. Amines, similar to alcohols, undergo alpha cleavage to generate a stabilized cation and a accompanying radical. Any questions on these fragmentation patterns so far? This is from the chapter 12 notes as we're doing a lab lecture on page 15. So continuing on, carbonyl compounds are quite interesting because they can undergo a rearrangement if there is a carbon-hydrogen bond 3 atoms away. This rearrangement involves the internal transfer of a proton to the carbonyl group, and this is called a McLafferty rearrangement. So we are, in effect, breaking the following 2 bonds in our fragmentation process. Carbonyl compounds can also undergo alpha cleavage, and this generates, again, a resonance stabilized cation. So these are common fragmentation patterns to be aware of when you start looking at spectra of compounds containing oxygen and oxygen functionalities. Does this make sense to everyone so far?
Professor, can you please show the alpha cleavage on the carbonyl group?
Sure. So in this case, we are breaking the following bond. So that in turn gives us let me find the best way of depicting it. So when we break the following bond, we end up with our alkyl radical and then our resonance stabilized aselenium cation. So we're breaking the following bond. So this is the bond broken during alpha cleavage. Does that make sense?
Yes, I can see it now. Thank you so much.
Perfect. Any other questions? Okay, so let's keep going now. And let's sort of summarize, well, how does mass spectrometry complement other techniques? Well, it's great at identifying the presence of chlorine or bromine from the M+2 peak. Mass spectrometry is great at allowing the molar mass to be accurately determined, and it allows us to estimate the number of carbons using the M+1 peak. Mass spectrometry provides us a rough skeleton for our molecule and a reasonable formula as well. However, mass spectrometry is often not used alone. It's coupled with other techniques that tell us about the functional groups and the arrangement of atoms in our molecule. And the next techniques that we're going to talk about, the next few techniques that we're going to talk about, focus on functional groups in our molecule and the connectivity of atoms in our molecule. So mass spectrometry really is just one part of our toolkit for structural determination. So let's talk about our next major structural elucidation technique, which is infrared spectroscopy. Okay, so we know that molecules have defined electronic states of different energies, right? When you looked at, for example, energy diagrams in Chem 101 and Chem 102, you know that if you take a molecule and you add energy in the form of heat or light of a specific wavelength, you can promote your electron. And in this case, you're looking at different electronic states. So most of the energy diagrams that you looked at in general chemistry concerned electronic states. And transitions between electronic states are observed in ultraviolet spectra, right? This is the principle behind why if you take a sample and you shine light with a range of wavelengths into your sample, some wavelengths of light are absorbed. Now, what is that energy being used to do? Well, when that energy is absorbed, we excite our molecule to a higher energy electronic state. And this is why different compounds are different colors. So we're used to this idea of electronic states. Does this idea of electronic states look familiar? When you talked about like atomic emission, for example, does that seem familiar to everyone?
Could you maybe do a brief explanation on that?
So electronic states, like similar to when we made molecular orbital diagrams, right? When we look at, for example, the HOMO and LUMO, these are describing electronic states for our molecule. Similar to how if you looked at the arrangement of electrons for like atomic energy diagrams, right? So if you have your S, P, etc., and you look at the arrangement of electrons in your atomic orbital diagram, in each case, the arrangement of electrons and the relative energy of electrons in our highest filled molecular or atomic orbital, these are describing electronic states. Two different molecular states that concern the arrangement of electrons and the orbitals occupied by electrons for that given state, right? So these are electronic states. And we see sort of the ramifications of these electronic states and transitions between these electronic states, because if we take a compound and we shine light through the compound, or if we add energy to the compound in the form of heat or an electric current, we can excite our compound to a higher energy electronic state, and then it can emit light. That's when we see atomic emission spectra. That's why different compounds or different metal compounds, when burned, yield unique colors. Or we can see absorption. So if you have like a red dye, for example, that dye is selectively absorbing certain wavelengths of light based on the difference between these electronic states. And when the compound absorbs light, it excites to a higher energy state. And this partially explains why different compounds, based on how their electronic states are arranged, will absorb different wavelengths of light. Does this sound familiar to everyone? Does this look familiar a little bit from general chemistry?
Yeah, thank you for that.
Okay. So we'll talk more about electronic states when we talk about ultraviolet spectroscopy. The important thing that's key to unpack is that for infrared spectroscopy, within each electronic state, there are a range of discrete vibrational states. So if we have our two electronic states, within those electronic states are a range of vibrational states. And these vibrational states each have a discrete energy. Now, why does this matter? Well, when we go from the ground state to an excited state, when we undergo an electronic transition, there are a range of viable transitions with slightly different energies depending on the initial and final vibrational state. So rather than just looking at electronic transitions and taking a somewhat superficial view of these electronic states, within each of our electronic states are a range of vibrational states. And so when we undergo an electronic transition, our electronic transition will have a different energy. We'll have a different difference in energy based on the starting, initial, and final vibrational state. Does that idea make sense? That we can break these electronic states into subtle vibrational states within that electronic state. Does that make sense? Now, as a result, this is why most ultraviolet spectra appear quite broad, because we have a range of different transitions that are occurring with slightly different energies for a given electronic transition. We'll talk more on that a little bit later on. Now, our goal in this chapter is to get a sense what is occurring for these vibrational transitions and how can we model or how can we explain these vibrational transitions. And the model that we're going to adopt is the ball and spring model. So if you've taken physics, this is going to sound pretty familiar, as we use a lot of terms commonly invoked when you talk about springs in physics. So if we think about a bond, like let's think about a carbon-carbon bond for a moment. We can visualize our carbon-carbon bond as a series of weights. So if we have our carbon atom, that'll be our one weight. The bond itself will be a spring, and the other atom will be a second weight. So we can imagine the two atoms as weights connected by a spring, which is the bond between our atoms. Now, this spring allows vibration, bending and stretching. So for example, if we wanted, we can stretch our carbon-carbon bond. We can just as easily take our carbon-carbon bond and bend our carbon-carbon bond. And we can manipulate and start to vibrate our carbon-carbon bond in different modalities, right? Just like two weights on a spring, just like if you've played with like a slinky or a paddle ball, for example, all of those are essentially a weight on a spring. So our bond can stretch, it can bend, and when we start to add energy to our system, the bond will vibrate with a defined frequency. So for example, if we look at our carbon-carbon bond, and if we add energy to our system, just like if you grab the end of a spring and you started to shake the spring, you're adding energy to the system, the bond will begin to vibrate. It'll begin to bend and stretch. So your carbon-carbon bond will stretch, and then it will return, and it can compress. And if we think about this cycle that's going to constantly repeat, once we put energy into our system, the bond will begin to vibrate. It'll begin to bend and stretch. If we looked at sort of, if we made a graph of our carbon-carbon bond length as a function of time, we would see that our bond length would oscillate. It would oscillate. So we'd see our bond expand and contract as it vibrates back and forth, right? Does everyone see how our bond is stretching, compressing, and vibrating with a defined frequency? And we can model this pattern as our bond bends and stretches, and we can look at the wavelength and the frequency of our vibration. And the main thing that I want you to know is that when energy is added to the system, the energy added is directly proportional to our frequency. So the more energy that we put into our system, in general, the higher our bond vibration frequency will be. Conversely, different types of bond vibration have different frequencies and different energies. Does that make sense to everyone?
Could you say that one more time?
So our bond, when we put energy in, it'll vibrate back and forth. That vibration, that bending and stretching cycle has a defined frequency. And that frequency, the frequency of vibration is directly proportional to the energy of our vibration. And different vibrational modes have different frequencies, and in turn, they have different energies. Does that make sense?
Yes, thank you.
Perfect. So, further, when energy is added to the system, a transition occurs to a higher energy vibrational state with a new defined frequency. Okay, so let's pretend initially we have our carbon-carbon bond. It is bending and stretching back and forth, and we add some more energy. We add additional energy in the form of heat or light. Light is the most operative one in this case. So if we add energy to our system, we'll transition to a higher energy vibrational state. And in turn, what that means is at a higher energy vibrational state, we have a higher vibrational frequency. So you can think about this intuitively. If you have like a slinky or a paddle ball, if you start to hit the paddle ball with a greater amount of force, if you start to use more force when you hit your paddle ball, you'll notice that the ball will begin to move back and forth on the spring at a faster rate, at a higher frequency.
Oh.
So we have our same carbon-carbon bond bending and stretching, but this bond vibration is going to be occurring at a higher frequency. So what that means is we're going to see a greater amount of this vibrational motion at our higher vibrational frequency. So rather than just sort of slowly bending and stretching, as we add energy to our system, the vibrational frequency increases, and this bending and stretching will occur at a substantially greater frequency. Does that make sense to everyone? So, for example, if we were to look at this in terms of cycles, so if on the same time scale we do one bending and stretching cycle, so this can be used to calculate our frequency. So wavelength, 1/wavelength is our frequency. If we are at a higher energy vibrational state, just for comparison, on the same time scale, we would see multiple cycles. So we'd see this same pattern of bending and stretching, but it would be occurring at a higher frequency.
Professor,
Yes.
what does that symbol below in the fraction 1 over and then the symbol equals V?
This is lambda, which is the wavelength.
Oh, okay, thank you.
Yep. So in this case, as we notice on the right, at our higher vibrational frequency, at our higher energy vibrational state, do we see at a higher energy vibrational state, do we see a larger or smaller frequency? Are we going through more cycles in the same amount of time? Is our bond vibrating back and forth at a higher frequency? Are we seeing this expansion and compression occur at a higher frequency? Yes. So our higher energy vibrational state has a higher vibrational frequency. Does this ball and spring model make a little bit of sense so far?
I have one question, Professor.
Yeah. Mhm.
I'm not sure if my Wi-Fi, but I'm not sure if you already talked about this, but like how does the spring behave whenever it's like double bond or triple bond?
So the double or triple bond, as we'll talk about this in a moment, but to answer your question, that affects the how rigid the spring is, and that affects how readily the bond can bend and stretch. And in general, the more rigid your bond, the higher the frequency of vibration, because it's by inherently a double bond and a triple bond, for that matter, has less freedom of motion, and as a result, the vibrations of double and triple bonds typically occur at higher frequencies.
So the more bond is the higher vibrational frequency.
The greater your bond order, the higher the observed vibrational frequency. Yes, that would be a reasonable statement.
Thank
Mhm.
you.
So now that we have this ball and spring model and we're starting to visualize our bonds in terms of this model, let's try to draw some conclusions from this. So first, as the mass of our bonded atoms increases, the frequency of vibration decreases. So if we compare, for example, like a carbon-hydrogen bond versus like a carbon-carbon bond. So a carbon-carbon bond has a frequency of around, for this sort of stretching, has a frequency of around 1,000 centimeter inverse. Comparatively, a carbon-hydrogen bond has a frequency of around 3,000 centimeters inverse. Now, the main difference, if we think about a carbon-hydrogen bond versus a carbon-carbon bond, is that hydrogen has a small atomic mass. So as a result, when we have a smaller atomic mass, we can a smaller atomic mass essentially implies that if we add energy and if we put energy into our bond, the bond can in turn vibrate at a greater frequency. The heavier our atoms, the lower our vibrational frequency. So the best analogy I can think of is if you have like a tiny piece of plastic hooked up to a spring, it's pretty easy if you put energy in for you to get that piece of plastic and to get that spring to start to move. However, if you decide to tie the same string to a car, for example, you're going to have a lot more trouble getting that spring to move substantially. So the heavier your atoms and the heavier your bonded atoms, the lower your vibrational frequency. Does that make sense to everyone? Further, since the energy of a vibrational state is proportional to frequency, the lower the frequency of vibration, the lower energy the vibrational state. So to show another example of these atom effects, so we know carbon-hydrogen bonds have a frequency of 3,000 centimeters inverse. Carbon-chlorine bonds have a vibrational frequency of 1,700.
Should we know these numbers, or should we just know that it's like orders of magnitude in difference?
Not these. I'll be talking about vibrational frequency values that you should note and memorize in a moment. The main thing that I want you to note in this case is that chlorine is a substantially heavier atom than carbon, and as a result, if we compare hydrogen to chlorine, chlorine is also heavier than hydrogen, so we observe a lower vibrational frequency for the carbon-chlorine bond. Does that idea make sense?
And what is the value for the frequency on chlorine?
For a carbon-chlorine bond?
Yeah,
Around 1700.
1700. Thank you.
Mhm. So the second major conclusion that we can draw from the ball and spring model is that as the bond order and bond strength increases, the vibrational frequency increases. This can be visualized by imagining two springs with different spring constants or tensions. So for example, if we think about a carbon-carbon single bond, you can imagine a relatively light spring. Well, if we have a carbon-carbon double bond, we now have a much more rigid spring. Now, the larger your bond order and the stronger your bond, the more rigid your bond will be. And as a result, if we think about the vibration, because this bond is more rigid, it has less freedom of motion, and as a result, the bond will vibrate at a higher frequency. That is why, for example, if we look at a carbon-oxygen single bond, it has a vibrational frequency of around 1100 centimeters inverse, while a carbon-oxygen double bond has a vibrational frequency of around 1700 centimeters. So as we noticed, as we increase the bond order, our vibrational frequency increases. So it's not just bond order. It would be better to phrase it as bond strength. Stronger bonds, more rigid, higher vibrational frequency. Does that make sense? Okay, so building off this idea that this effect is based on bond strength, a carbon-hydrogen sp3 bond has a frequency of around 2900 centimeter inverse. A stronger carbon-hydrogen sp2 bond has a frequency of around 3100 centimeters. This distinction is very important, and we'll be seeing this distinction again in order to help us determine the structure of our suspect compounds. So, just to give an example, yes.
Professor, I have a question.
Yes.
Is the CH bond stronger because it's sp2 compared to the sp3?
Yeah, so carbon-hydrogen bond attached to an sp2 carbon. So for example, like in this example, the carbon-hydrogen bond attached to an sp2 carbon is inherently stronger because if we think about an sp2, if we think about an sp2 orbital, it's a shorter, lower energy orbital. And as discussed in 113, it in turn leads to a shorter, lower energy bond. So a carbon-hydrogen bond attached to an sp2 carbon will be shorter and stronger than a carbon-hydrogen bond attached to an sp3 carbon. Does that make sense?
Yes, thank you.
Mm-hmm. And does this idea look familiar from 112?
Yes.
Yes.
Perfect. Just look at the question in the chat. There's actually a pretty clear demarcation and pretty clear separation between many of these vibrational frequencies. So even though they look pretty close at first glance, they're pretty easily distinguishable for most common functional groups. So what we're going to do next is we're going to talk a little bit about how do we actually begin to measure an infrared spectra? What are we measuring in this process? And why do we choose an infrared radiation source? So to think a little bit about spectroscopy, we have to first look at the electromagnetic spectrum. Now we know that radiant energy is proportional to the frequency. Different types of electromagnetic radiation are classified by their frequency and corresponding wavelength ranges. So as we notice, infrared radiation compared to visible light is a lower energy radiation source. So infrared radiation is lower in energy than visible light. Now, the reason why infrared radiation is used is because infrared spectroscopy aims to observe vibrational transitions. And these vibrational transitions are lower in energy than electronic transitions. Thus, we need an infrared radiation source as it is a lower energy radiation source and it's in the wavelength range and it's in the energy range that matches our vibrational transitions. So then, if we take our sample and we expose it to infrared radiation, certain wavelengths and frequencies of light are absorbed. And in turn, that can tell, and these certain wavelengths and frequencies of light are absorbed based on the vibrational frequency of bonds in our molecule. So from the frequencies absorbed, we can figure out the functional groups in our molecule. This is the central premise behind infrared spectroscopy. Does that make sense to everyone? Okay. So, just to reiterate that premise, based on the wavelengths of infrared radiation absorbed, the bonds and functional groups in the molecule can be assigned based on their unique vibrational frequencies and energies. So, infrared spectroscopy will often give an output of an absorption spectrum, where we have measured the different wavelengths and frequencies of light absorbed. We commonly report our frequencies in terms of wave number, which is centimeter inverse. And the key thing to keep in mind is organic compounds, based on their different functional groups, will only absorb energy of certain wavelengths. And each of the downward peaks that we see correspond to absorbed energy and absorbed infrared radiation. This absorbed infrared radiation will depend, and the exact frequency of the absorbed infrared radiation will depend on the bonds and functional groups in our molecule. So the specific infrared radiation absorbed by an organic molecule is related to its structure. And based on the wavelengths of infrared radiation absorbed, the bonds and functional groups in our molecule can be assigned based on their unique vibrational frequency and energy. So what we're going to do now is we're going to unpack common vibrational frequencies, and we'll talk through how to interpret different infrared spectrum. So let's talk a little bit about vibrational energy modes. And this is really important to consider because the same bond can have multiple vibrational frequencies based on its different vibrational modes. So bonds can undergo different types of vibrational excitation and access different vibrational modes, each with their own vibrational frequencies and energies. So examples of this would be symmetric and asymmetric stretching, in-plane bending, and out-of-plane bending. Each of these unique vibrational modes and vibrational excited states have discrete energies, frequencies, and observed wave numbers. We see this, for example, because for the same carbon-hydrogen bond, it exhibits a stretching frequency of around 3000 and a bending frequency of around 1300 centimeters inverse. So the vibrational mode can have a discrete energy and a discrete vibrational frequency. Does that make sense to everyone? This is a really important point. So multiple vibrational frequencies can be ascribed to the same bond.
Professor,
Yes.
I'm just confused on like, will we be able to identify which vibration will they go through, like symmetric or anti-symmetric?
Yes, because it has a tabulated and defined vibrational frequency for each functional group.
Can you please explain how we're going to identify what stretching and bending will they go through?
Because in the infrared absorption spectra, for example, you will see defined. So, for example, you will see defined regions where a defined frequency of light is absorbed, for example, at around 3000 centimeters inverse, and an absorption of infrared radiation with a frequency of 3000 centimeters inverse directly corresponds to the absorption associated with a carbon-hydrogen bond, and more specifically, a carbon-hydrogen stretch. So all of these characteristic absorbance frequencies are tabulated, and by observing a spectra and noting the different absorbance, the different frequencies of light absorbed, which directly correspond to our vibrational frequency, you can in turn figure out what functional groups are present and the type of vibrational mode that functional group is engaging in. Identifying the exact vibrational state is not as important as utilizing the absorbed frequency of infrared radiation to figure out the functional group identity. So for example, it's not particularly important that this 3000 is a CH stretch. It is important that the absorbance of light with a frequency or wave number of 3000 centimeters inverse corresponds to a CH functional group. Does that answer your question?
That actually did. Thank you so much.
Okay, perfect. So similar functional groups absorb at about the same energy and intensity. And there's a table of infrared absorptions in your book on table 12.1 that can be used to confirm the existence of a functional group in your molecule. Now, you do not want to just play a matching game. That's not necessarily the best way to go about interpreting an infrared spectra. So what we're going to do is we're going to look at So I provided also another table of IR absorptions. You will have to be familiar with all of the values in this table as they do come up in structural determination. With that said, there's ways to parse this data to make it a little bit more manageable. So I have the table provided on the 2 pages of the notes. What we're next going to do is we're going to talk about how do we apply this information to interpret an infrared spectrum. Okay, so you will have to be familiar with all of those absorption values, but there's a fast way to go about breaking apart an infrared spectra to identify functional groups quickly. So first, let's really make sure the purpose of this exercise is clear. Infrared spectra are primarily used to identify functional groups found in the molecule. Infrared spectroscopy serves as a complementary tool to other analytical methods. IR is often used deductively to confirm or deny the presence of a functional group. So because it's often used in a deductive manner, you're often looking at an infrared spectra to confirm or deny whether or not a functional group is present. Did I form the alkene that I wanted? Did this reaction get rid of my alkene? Did this reaction generate this alcohol functionality? These kinds of very binary tests are very important to consider, and that makes IR a very useful tool. So the point I'm trying to make here is rather than checking for every functional group and every observed frequency, it's often efficient to identify possible functional groups and check for their frequencies in your infrared spectra. For example, if you have a hydrocarbon, there's no reason to look for an amine functional group if there's no nitrogen present in your formula, right? So you can break down the infrared spectrum into major regions. So 5,000 to 1,000 is the fingerprint region. Oftentimes you're never going to look here. It doesn't have a lot of useful information. It's often just a mess. You can see around 680 to 860. That's useful for aromatic systems. So I see a question in the chat. Yes, IR is a non-destructive technique. Yep. You can reuse your sample after taking an IR spectra. Yep. The other region to look at is 1650 to 1800. That's the CO double bond stretch. Super useful. 2100 to 2600, I like to call the triple bond region, or like an SP region, as you really only see nitriles and alkynes in this region. 2850 to 3100 is the CH stretch region and allows us to determine whether we have sp2, sp, or sp3 carbon-hydrogen bonds. 3200 to 3400 is the OH stretch. 3300 to 3500 is the NH stretch. And 3300 is a unique frequency because it indicates an sp-CH bond. We'll be going through each of these regions in detail, but it's always important to start to visually map these different absorption frequencies in these different regions of the infrared spectra onto an actual plot. Does this make sense to everyone so far? Any questions? Yes, absorbance and transmittance are directly related. It's not necessarily the exact percent transmittance or the exact absorbance. It's not related to the amount of that functional group in your molecule. It's related more towards the induced dipole and how readily that functional group will undergo a vibrational transition. And we'll talk about that later on, actually. So we'll address that question in a little bit. So when we talk about peak intensity, the intensity of an observed IR absorbance is based on the strength of the bond dipole moment changes when the bond vibrates. So inherently, bond vibration results in changes in the bond dipole during vibration. So for example, if you have a carbon-oxygen double bond, as it bends and stretches, you're going to have a slightly modified bond dipole. And these changes in bond dipole during vibrational transitions are critically important. Well, first and foremost, they're necessary in order to actually observe a vibrational transition. But further, the greater the change in bond dipole moment during vibration, the stronger the observed IR absorbance peak. So generally, bonds with strong dipoles experience large changes in bond dipole during vibration and exhibit strong, sharp absorbances. So for example, if we look at the CO double bond stretch, it's a very sharp, narrow peak centered around 1700. So oftentimes, if you have a ketone or a carbonyl functionality, it's a super obvious peak. You almost can't miss it. And the CO stretch is around the 1700 region. Does that make sense? Okay, so looking at peak widths. Peak widths, it's a little bit more interesting. So hydrogen bonding and exchange leads to broad OH and carboxylic acid peaks as hydrogen bonding affects the OH bond strength. So it's important to think when you think about a hydrogen bond, it's best not to think of it as a static entity because molecules, especially in solution, they're not static entities. They're constantly moving about. There's a baseline amount of molecular motion, right? And as a result, we have hydrogen bonding interactions forming and breaking, right? And these hydrogen bonding interactions directly impact our OH bond strength. And when we have a large sample of molecules on the IR data collection timescale, we observe a range of OH bond strengths as molecules are rapidly engaging in hydrogen bonding. As a result, we see a very broad peak because remember, the frequency is proportional to our bond strength, right? And if we have a range of observed bond strengths for our alcohol, we will often see a very broad peak. Does that logic make sense to everyone?
Yes.
Okay, so the presence of an alcohol or carboxylic acid is indicated by the broad OH stretching peak. So we'll see a broad peak centered around 3200 to 3300. So for example, here's a spectra of 1-hexanol. The OH stretch peak is sensitive to solvents, and in non-hydrogen bonding solvents, a minor sharp OH stretch peak can be observed right here. So this solvent dependence is useful because if you change the solvent and you happen to get rid of that sharp peak, that's another piece of evidence supporting the presence of an alcohol. Does that make sense? Okay, so continuing on, This sharper OH stretch comes from the alcohol not participating in hydrogen bonding. And that's why we see this two-component peak. The presence of a carboxylic acids are pretty obnoxious in the IR spectra. It's pretty hard to miss a carboxylic acid because they have a very broad OH stretching peak centered around 3,000 centimeters inverse. Further, as we learned previously, a carboxylic acid, in addition to having a OH bond, also has a carbon-oxygen double bond, and that carbon-oxygen double bond has a characteristic CO stretch. Where does that stretch show up? Would anyone like to comment? Where is the CO double bond? Where's the carbonyl vibrational frequency? The super sharp peak. 1700, yep, right here. That is our CO stretch. Well, this is our OH stretch. So obviously, if you don't have the CO double bond stretch, you can't confirm the presence of a carboxylic acid, right? So this broad peak coupled with a CO double bond stretch gives us two pieces of information to verify we have a carboxylic acid. Does that make sense? Does everyone understand how we need two pieces of data here to support our argument?
How did you determine that the 1 by 3,000 was the OH stretch?
Because, well, first it's a very broad peak. So it's, let me sort of put a box around it. This entire thing, well, probably up to here is our OH. It's a super broad, very large peak, and it's centered around 3,000 to 3,200. And so, sorry, I'm somewhat confused by your, are you asking why did I pick that specific peak in that range? It's, so the OH stretch has a defined frequency of around 3,000 to 3,200. In the case
okay.
of carboxylic acid, it's a little bit lower on the frequency range, and carboxylic acids are characteristically broad. The other thing that would distinguish a carboxylic acid from a alcohol is that the carboxylic acid will inherently exhibit this CO double bond stretch. Does that answer your question?
Yeah, if it's in the 3,200 range and then it's a broad peak, then it must be the OH.
Yes. And
Okay.
coupled with the second piece of information, if we see a carbon-oxygen double bond stretch at 1,700, that tells us it's a carboxylic acid rather than an alcohol.
Okay, thank you.
Does that make sense?
Yes, it did. Thank you.
Perfect.
Professor, one quick question. I'm
Yes.
sorry. So what if in the molecule there's an OH present, but there's also a C double bond O present? How will the graph be, like how will the graph behave if they're actually not connected to one another?
So if they aren't connected, then this OH stretch wouldn't be as broad. Like if you compare an alcohol, notice how the alcohol, the peak is a little more narrow. Further, it's centered around 3,200 versus 3,000. So there's a subtle difference in, well, that's not very subtle at all. Actually, it's 200 centimeters inverse. And you see this characteristic side peak as a solvent effect. Does that answer your question? So first, it's the actual vibrational frequency itself for the OH stretch. It's different if you compare an alcohol to a carboxylic acid. And further, an isolated alcohol would also exhibit this side peak behavior where some of the hydroxy groups within your alcohol are not participating in hydrogen bonding.
Thank you.
Mm-hmm. Any other questions I can address? Okay, so let's keep going from here. And I'd like you to tell me, let's look at these two together. So I'm zooming out just so that way we can observe the spectra. These are genuine spectra, similar to what you'd see in the laboratory. And I'd like you to tell me for spectra A and B, is the molecule an alcohol or a carboxylic acid? So looking at these two spectra, I'd like us to take about 4 minutes and identify whether we have an alcohol or carboxylic acid in each of these two spectra. And please try to include an explanation for why. Make sure your argument is supported with the vibrational frequencies observed in each spectra. So we're starting to see some students commenting in the chat. Let's try to get a few more comments. So we notice one student noted the presence of this peak at around 1700 and a peak at around 3200 centimeters inverse. And so they concluded that a carboxylic acid was present. What does everyone think about this? Do we agree with this explanation? And as we notice, this peak for our OH stretch is very broad. Okay, that's a perfectly reasonable assignment for structure A. What about structure B? What do we think? For structure B, do we have an alcohol or a carboxylic acid? What do we think for structure B? So we notice that there's the absence of a functional group. There's nothing. There's no carbon-oxygen double bond stretch. Further, we see this peak for our OH stretch centered around 3200 centimeters inverse. And we see this little side peak. So in turn, we conclude that this structure is an alcohol. Does this example make sense to everyone? Does this set of examples make sense? Any questions on these two? Okay, so let's keep going. Let's look at some common functional groups now, and let's consider alkanes, alkenes, and alkynes. So alkanes, alkenes, and alkynes are distinguishable, both in terms of formula and in terms of infrared absorbances. Alkanes, we see a characteristic CH stretch at around 2850 to 2960. Your carbon-carbon single bond stretch is 800 to 1300. Alkenes, there are two distinct peaks that we need to consider. The CH stretch from 3000 to 3100. So the CH sp2 stretch has a frequency greater than 3000. 3000 is an important dividing line to consider. And the carbon-carbon double bond stretch occurs at around 1640. So if you have a double bond, you would need to see both of these characteristic frequencies. Now, one thing that I would like us to consider, if we have an alkene that looks like this, what signals would we see? So if we have a tetrasubstituted alkene, what signals would we see?
The The carbon to carbon double bond.
Yep, yep. So we would only see the carbon-carbon double bond stretch from 1640 to 1680. We would
Wait, why
not,
only that?
could you repeat that, please?
Why only the carbon to carbon double bond?
Ah, yes, that's a very good question. So this 3000 to 3100 signal is a CH stretch, right? So it's a CH
Yeah.
stretch when the carbon is sp2 hybridized, right? So
Yeah.
looking at this structure, do we have an sp2 carbon attached to a hydrogen?
No.
Exactly right. And because we don't have that carbon hydrogen bond, we wouldn't see that stretch. So it's important to check for both of these absorbances, because in some cases, if you have a tetrasubstituted alkene, you would only see the 1640 to 1680 signal. Does that make sense?
Yeah, it does.
Perfect. For alkynes, a similar premise, the carbon-carbon triple bond stretch occurs from 2100 to 2260, while an sp-CH stretch has a very unique absorbance at 3300. Similar to the alkene, an internal alkyne, so something like this, for example, what signals would we see for an internal alkyne? What signals would we see?
The 2100 to
Yep.
2260.
Yep. Would we see a signal at 3300 for this structure?
Nah.
Exactly right. We are missing that carbon hydrogen bond. And by definition, we would only see an absorbance, we would only see a vibrational frequency associated if that bond is actually present in our molecule. Just important to consider, as this is like a component of a slightly more difficult question that you can ask for IR spectra. And students, sometimes they look for the CH bond, they forget to look for the CC stretch, and then they get stuck. So it's always important to bring up these internal and tetrasubstituted cases. Any questions on this so far? So when you look at the 2800 to 3300 region, you'll often see this dividing line occur where you have your sp3 peaks on the right of the 3000 centimeters inverse mark. Your sp2s will be on the left, and then all the way out to the side will be your spch. So by looking at the 3000 centimeter inverse dividing line, you can identify potentially whether you have an alkene, alkane, or an alkyne. And of course, then you'd have to do some follow-up in the 1600 to 2200 region, right? The 2200 region, that's your carbon-carbon triple bond. Your 1660 region, that's your carbon-carbon double bond. Does this make sense to everyone so far?
What's the centimeter inverse for SP2? Unless I-
SP2CH, it's around 3000 to 3100.
Okay, thank you.
Yep. Any other questions I can address? Okay. So, elaborating a little bit more on this 2900 to 3100 region, it's very useful to identify the presence of an alkane, alkene, or aromatic functionality. For example, if you only observe sp2CH peaks, then an aromatic is likely present. Do you notice how we don't see any absorbances So if we don't see anything, we see nothing less than 3000 in this region. So as a result, we have no sp3ch bonds in this molecule. So that's a strong piece of evidence supporting that we have an aromatic ring. If you have a typical for example, if you have your typical alkane, you'll notice that all of the peaks are less than 3000 centimeters inverse. So as a result, we only have sp3ch bonds. If we have an alkene, notice we observe an sp2 CH bond absorbance at around 3100 centimeters inverse. So an absorbance above 3000 provides strong evidence that we have an alkene present in our molecule. Of course, you can also back this up by looking in the 1600 region as well. Does this make sense to everyone so far? Perfect. So let's look at some examples. So in the first case, we'll see and we'll ask ourselves, does the compound have an alkane, alkene, or an alkyne? So in this case, we clearly have an alkene supported by the presence of this sp2ch around 3100 and our carbon-carbon stretch at around 1600 centimeters inverse. The magnitude of the absorbance in this case, it's not due to the nature of, so the benzene carbon-carbon bonds are closer to that of 1.5 bonds, and that does affect the carbon-carbon bond stretch, but it doesn't affect the CH stretch as much. Did that answer your question in the chat? Okay, so now that you've seen me do a representative example, let's take a look at these two. And I'd like you to look at example A, and I'd like you to tell me, does the compound have an alkane, alkene, or an alkyne, and why? Provide evidence to support your conclusion. So for compound A, does it have an alkane, alkene, or an alkyne? So let's take about 2 to 3 minutes on this example, and I'd like to see some responses in the chat. So we see some students mentioning this 3000 dividing line. As you see, we see no peaks greater than 3000 centimeter inverse. And as a result, we can conclude that we have an alkane. For further evidence, just because to rule out the possibility we have an internal alkyne, we also see no carbon-carbon triple bond stretch at 2100, and we also see no carbon-carbon double bond stretches at 1600 centimeters inverse either. So these three pieces of evidence allow us to conclude that we have an alkane. Does that make sense to everyone?
I have a question. So you said there was no inverse peak on 1600.
Yes.
So like
there's no
that tiny
absorbance.
peak there, it doesn't count as one, right?
Could you repeat that, please?
That tiny peak near the 1500, it doesn't count as one. It's not.
Yeah,
It's not steep enough.
that's 1500 though, which is quite a different range compared to.
Oh, okay.
Does
All
that
right.
make
Yeah.
perfect? So these ranges are generally pretty precise. And so like a difference of 100 centimeters inverse is big enough for you to differentiate two functional groups based on their absorbance. Just like, for example, we concluded there was no sp2 or sp-CH bonds because we don't see any absorbances above 3000. It's always important to check it's always important to check the alkyne and alkene region, because if you have an internal alkyne or a tetrasubstituted alkene, they wouldn't exhibit a CH peak, but you would see the CC peak. So it's always important to do this double check.
Professor?
Yes.
So for alkanes, it can exhibit one or the other, right? In terms of the CH or the CC?
Alkanes, they would exhibit a CC single bond, which isn't in the 1600 or 2100 region. They're close. They're at much lower wave number values.
Oh, okay.
Yeah.
Oh, I'm sorry. I read that that box wrong in the middle. I misread that. It said alkyne. Excuse me.
Yeah, sorry about that. I initially had the label that this whole structure was considered an alkane, but when I put the box in, I changed it to alkyne because this region is the alkyne region. This molecule, this formula, this spectra corresponds to an alkane. Does that clarify? Does that make sense?
Yes, it does.
Okay, perfect. Okay, last example of this group. Do we have an alkane, an alkene, or an alkyne? And what two peaks give this away? Don't be shy. So we have an alkyne, yep. And what two peaks give it away? Let's reinforce this idea. So the 3300, that's the CH-SP stretch. And we see a peak at 2100, which is the CC triple bond. You want both peaks to be present if you're supposing you have an alkyne. Yes.
Professor,
Yes. Mm-hmm.
so for the 2100 peak, does it have to be like a really like deep peak, like has to go all the way down, or
No. The peak intensity is not related to the amount of a functional group. Just as long as you observe an absorbance in that region, that is evidence enough for that functional group.
Okay.
Does that make
And
sense?
it has to have both the 3300 and the 2100 peaks to be an alkene, right?
To be an alkyne, yes.
Oh, alkyne. Alkyne.
Any other questions that I can address?
Professor, do you mind scrolling up a little bit so I can see the last one? Okay, thank you.
Perfect. So let's look at an example that's a little more practical. So suppose you run a reaction in the lab and you look at the epoxidation of cyclohexene and you collect an IR spectra before and after the reaction. Which spectra would correspond to the reactant and which spectra is the product? So you're looking at the following reaction. So a typical epoxidation to generate an epoxide of cyclohexene. And given these two spectra, A and B, which spectra corresponds to cyclohexene and which one corresponds to the epoxide? So let's take about 3 to 4 minutes to work on this example. And then I'd like to see some responses in the chat. So I'd like you to tell me which of these two spectra corresponds to our reactant alkene and which one corresponds to our product epoxide? So we see one student noting that there's nothing in spectra A in the 1600 to 1700 region. So then we don't have a carbon-carbon double bond. That is proof via the absence of an observed signal. We also have proof via the presence of an observed signal for B, because as we notice, if we draw a dividing line around 3000 for B, we observe signals greater than 3000 centimeters inverse, and that corresponds to an sp2ch stretch. What's our follow-up piece of evidence? What's our follow-up piece of evidence? What's our second peak that we should note? Is that all? I'd say it's closer to 1680, which is our carbon-carbon stretch. If you're having trouble figuring out the exact absorbance value, it's important that you get out a ruler or another device just to make sure. Yep, but this 1640 to 1680 tells us we have a carbon-carbon double bond, so we can definitively assign B as cyclohexene. And as a result, because A, we see no carbon-carbon double bond and we see only CHSP3 stretches, we would conclude that A is our epoxide. So as you notice, by looking at changes in our infrared spectra before and after the reaction, we can confirm or deny the presence of a reaction. Does that make sense to everyone? Any questions on this idea? The epoxide, you'd probably see it in the CO stretch, and that's probably around 1300. It's really hard to, once you start getting towards the fingerprint region. The CO stretch is pretty hard to detect. Did that answer your question? Perfect. So let's keep going now and let's look at aromatic compounds. So aromatic compounds, they have a weak CH stretch at around 3000. So it's a little lower frequency than your typical sp2ch stretch. They have weak absorptions from the 1660 to 2000 range, and then medium intensity absorptions from the 1450 to 1600 range. So the main differentiating factor, if you compare an aromatic system to a typical alkene, first, we have a slightly lower frequency for our CH stretch. And further, we see multiple CC stretching frequencies. Does that make sense? So for example, if we look at the following compound that contains an aromatic ring and an alkyne, we see our aromatic peaks. Notice how all of our absorbencies are greater than 3000, just barely. These are our sp2ch stretches. We see a peak at 3300. What is that peak at 3300?
Is that the double bond? Or
3300, what range does that correspond to?
alkynes?
We have an alkyne.
Oh, okay.
Oh, please go on. What do we think? 3300?
The 3000 wasn't the triple bond CH bond?
Yep, it's the CH with an sp hybridization. Does that make sense? Perfect. So what other peaks provide evidence that we have an aromatic ring? What other peaks do we see?
Can we see the C double bond C?
Yes, and we see a range of peaks, the first of which are a set of peaks in the 1660 to 2000 centimeter inverse range, as well as these medium peaks in the 1450 to 1600 centimeter inverse range. Finally, the one last peak that I want you to pay attention to, we see a peak at around 2100 centimeter inverse, which is our carbon-carbon triple bond. So does everyone see how the aromatic peaks fit in the IR spectra?
Yes.
Perfect. So let's keep going now, and I'd like you to try and match the following spectra to each compound. So I'd like you to match bromobenzene and 2-hexene to the following two spectra that we'll label as A and B. So we have the names bromobenzene and 2-hexene, and I'd like you to match the spectra to these two names. We'll take about 3 to 4 minutes on this example, and I'd like to see some responses in the chat. So, what do we think? Does anyone have any initial thoughts? Let's really focus on assigning peaks in each of our spectra and looking for characteristic peaks that we can use to assign the identity of our compound. So if we're thinking about bromobenzene and 2-hexene, what peaks should we be looking out for? Are there any peaks in the spectra that anyone wants to point out?
From the last slide, from the last presentation, we look at the benzene one, where is the sp2ch stretch peak?
Yep. So we see sp2ch stretches, and they're greater than 3000 centimeter inverse. Yep. Okay. Now, looking at bromobenzene, someone also notes these sets of weak peaks from 1660 to 2000. These are the aromatic CC double bonds. Yep. What is another proof via the absence of a signal? If we look at bromobenzene, what signal would obviously be absent? So if we compare these two compounds, what signal will be present in one of these samples but absent in the other? So we noted these aromatic peak signals. What else?
The carbon-carbon double bond
So
and the alkene.
Could you elaborate on that a little bit?
Like since the aromatic bond doesn't have a carbon to carbon double bond, the alkene has a carbon-carbon double bond. So we might see a peak around 1640 to 1680.
You're correct in noting that the carbon-carbon double bond stretches are different. The aromatic ring does have carbon-carbon double bonds, but those signals have a very different pattern compared to an isolated alkene. So for your alkene, for example, we see a signal around 1640, which is about right here. That's our carbon-carbon stretch. Well, for an aromatic ring, we see peaks from the 1660 to 2000 region and in the 1450 to 1600 region. So we see these weak peaks and these medium peaks. And this is an important aromatic pattern and an important signpost. We have an aromatic ring. So that is an important point to bring up. Aromatic double bonds have different stretching frequencies than normal alkene double bonds. What else? What else? The bromine carbon bond, yeah, that's probably going to be in the fingerprint region. That's not super diagnostic. You could run a mass spec and that would probably provide you a more definitive proof you have a bromine. What else? Let's focus on what is present in one structure that's absent in the other. We have pretty good proof so far that we think the spectra A is bromobenzene. Why is spectra B hexene? So we see, say, side peak on B. What do we mean by that? So in the 3000 region, are you referring to this peak here?
Yeah.
Okay, so we see a peak in the 3100 centimeter inverse region. That implies we have an sp2ch. Okay, but doesn't benzene have sp2chs?
Yeah.
Yeah, okay. So then we notice a student mentioning that we see a lot of peaks below 3000. So we see a lot of absorptions at less than 3000. Now, why is that important? What does an absorbance that's less than 3000 tell us? What type of bond do we have?
Okay, alkanes.
Yep, we have an sp3ch stretch observed, and as a result, that tells us we have an alkane region in our molecule. And because of that, which of these two structures actually has an sp3ch bond? Which of these structures? What's the only structure with an sp3ch bond?
The hexene?
Yep, exactly. Bromobenzene doesn't have an sp3 carbon in its structure. Does that make sense to everyone? Does that argument make sense? Only one of our structures has an sp3ch bond, and as a result, only one of our structures, we would see these absorbances less than 3000 in the 2800 region. Does this example set make sense to everyone? Does everyone notice how we have the tools to distinguish an alkene from an aromatic system?
Professor, I have a question. Wouldn't the carbon that's not in a double bond be considered sp3?
You mean like, for example,
For the bromobenzene.
yeah, so looking at the structure of bromobenzene,
Yeah.
which carbon are you talking about? Oh, sorry.
The one that's not involved in a double bond. There's about 2 on the line structure that you drew.
So let me put numbers 1, 2,
Okay.
3, 4, 5, 6. Which one are you referring to?
4.
4?
Yeah.
Wait, isn't carbon 4 has a double bond with carbon 3, correct?
Yes, but wouldn't it have sp3 hybridization? Because there's another hydrogen coming out of it.
So if we have
Or
a
no?
carbon with 3 sigma bonds and 1 pi bond, that would have an sp2 hybridization.
Oh, okay. I
Does
see.
that make sense?
Yeah, thank you.
In
I got
aromatic,
confused.
all of our carbons in this ring are sp2 hybridized, and as a result, we'd only see sp2ch stretches.
Okay, thank you.
Important point to entertain though is we have something like toluene where you would have an sp3 carbon here. The aromatic peaks can still be distinguished by virtue of the fact that you see this major minor pattern and these medium and weak peaks are present. Does that make sense to everyone? So these medium and weak peaks associated with our carbon-carbon double bond stretches are super diagnostic for aromatic systems. Is that important to consider? Perfect. Okay, so let's look at the next functional group to consider, which are alcohols and amines. So alcohols, 3400 to 3650, usually broad and pretty intense. The amines, 3300 to 3500, they're sharper and less intense. Now, the 3200 centimeter inverse region is useful to indicate the presence of an amine. And the other thing I'd like you to note is if we compare a primary to a secondary amine, primary amines and amides give two unique NH stretching signals due to symmetric and asymmetric stretching modes. It's not that we have two hydrogens, it's that there are two possible vibrational modes. We can have asymmetric and symmetric. Now, why is this important? Well, if we look at a secondary amine, secondary amines and amides only give a single NH stretching signal. Now, just to follow up on this idea, and just to make sure everyone's paying attention on this, what if we had a tertiary amine? What if we had a tertiary amine? What signal would we see for a tertiary amine?
Will it be secondary?
Would we see a signal at around 3200? Would we see an NH stretch for a tertiary amine? No. So we'd see no NH stretch, right? Because is there a nitrogen-hydrogen bond? It's just important to consider the reason why tertiary amines and amides aren't mentioned is because there's no NH bond in a tertiary amine or amide. Does that idea make sense to everyone? Does that concept make sense?
So why would you need like an H bond in the stretch?
Well, to phrase it another way, this NH bond has fine vibrational frequency of around 3200, right? And if we don't have an NH bond, if we don't have that bond present, we wouldn't observe that frequency, right?
Oh, okay. So it just wouldn't be there?
Yes, so we wouldn't see
Okay.
any signal in that 3200 region because there's no bond present that's going to be absorbing that frequency of light.
Okay.
Does
All
that
right,
make
got it. Yeah,
Perfect.
thank you.
Further, we know that amine signals are going to be more intense than amide signals. Further, an amide, of course, which looks a little bit like this, can be differentiated because it has a characteristic carbon-oxygen double bond stretch with a vibrational frequency of 1700 centimeters inverse. So we can differentiate an amine from an amide based on the carbonyl stretching frequency. Does that idea make sense to everyone? Similar to what we did with the carboxylic acid, right? We can tell the difference between an amine and amide by looking for the CO double bond stretch. Does that make sense to everyone? Any questions so far? Okay, so let's keep going now, and let's look at the following 3 spectra. Let's zoom out a little bit. Oh, one moment. So let's look at the following 3 spectra and try to answer the following question. Which spectra has an alcohol? Which spectra has an amine? Or does the spectra contain neither an alcohol or an amine? So looking at these 3 spectra, I'd like you to tell me, whoops, one moment. So for A, B, and C, I'd like you to tell me which of these spectra contain an alcohol, amine, or neither. And let's take about 5 to 6 minutes to work through this example, and then we'll discuss. And don't be shy to share your thoughts or any proposed peak assignments that you have for any of these 3 spectra. So which of these spectra have an alcohol? Which one has an amine? Do any of these spectra have neither? And make sure you can back up your assertion with some absorbance frequencies and some peak assignments. So we have one student noting, so for A, we have a few opinions on it in the chat. We have some students mentioning neither, some who think it's an amine. We see a lot of consensus for B, that we likely have an amine in structure B, because we see a peak in the 3300 region. And we see this split 2-component peak, which is typical for a primary amine. Looking in the chat, we also see students talking about A. We see a lot of students commenting that A looks a lot like an alcohol. And they noted that there are a few pieces of evidence to support their conclusion. First, they see this peak in the 3200 region that is quite broad, and they also see this side peak. What does the class think of our discussion so far? Do we agree with the points that the class has made? I'm just reading off what people are saying in the chat for right now. Do we agree with the points being made for A and B? Any questions? Does anyone have a rebuttal argument? Does anyone disagree with any of these assertions? It's okay. I'm just voicing what the class is saying in the chat. It's okay to disagree necessarily.
I have a question. So like on the given range for the peaks for amine and alcohols,
Yep.
it says the OH is going to have 3400 to 3650.
Yes.
And then NH is going to be 3300 to 3500.
Yep.
Like what if there's a number that falls in between those 2 ranges? Like let's say
Then it's based on peak shape.
Yeah.
So
really? Okay.
Alcohols are generally broader. You notice how the
Alcohols
alcohol
are
is broader?
Okay. Yeah.
Further, alcohols typically exhibit the side peak in hydrogen bond solvent, and this side peak indicates alcohol not participating in hydrogen bonding. So this is the characteristic peak shape associated with an alcohol. Does that make sense?
Okay. Yeah.
So the peak shape and the distribution of peaks also provide evidence for a functional peak.
Okay, I see. Thank you.
The other piece of evidence that you can note is that for a primary amine, these primary amines are the only functional group that exhibit these two component peaks due to both the symmetric and asymmetric stretching.
Professor, I have
Okay.
a question.
Yes, please go ahead.
So for letter A,
Yep.
it doesn't necessarily have to start at the 3400. It could spread, as long as it spreads out towards it, it counts as an alcohol.
Yes. Alcohol
Okay.
amine peaks can shift around. They have pretty broad ranges overall compared to most functional groups, and it's due to their pretty broad ranges that they're quite distinguishable. Does that make sense?
Yes.
Perfect. So structure C is a little interesting. What does everyone think about structure C? Do we have any alcohols or amines in structure C? What do we think? So students note that we observe an absorbance greater than 3,000, and we see a peak in around the 31 centimeter inverse range. That corresponds to an sp2 CH bond. We don't see anything in the alcohol or amine region, so we conclude that we likely have an alkene with no alcohol or amine. Does that make sense, Tara?
I have a question.
Yes, please go ahead.
So since that peak is pretty tiny, the one that looks like it's about 3200, it wouldn't count as an amine because it's too small, or
It has to be a reasonably significant absorbance. Alcohols and amines have a medium absorbance value typically.
okay, got it.
Compare C to B and A, you don't see an absorbance nearly the same magnitude. And although it is structurally dependent, these kinds of super minor peaks outside of aromatic systems, it's really unlikely that you have an alcohol or amine if it's absorbing with that minimal amount. Does that make sense?
Yes, thank you.
Perfect, perfect. So let's look at this next example. In this case, we're asked to match the following spectra to the following names. So we have N-ethylbutylamine, which looks something like this, and butylamine, which looks something like this. And based on that information, based on these two structures, I'd like you to tell me and match each of these structures 1 and 2. I'd like you to match structure 1 and 2 to spectra A and B. So let's take about another 3 to 4 minutes to work on these examples, and then we'll discuss together as a group. So I'd like you to tell me which of these spectra correspond to which compound and what peaks will support your discussion. What peaks will support your argument? So we see students mentioning that if we compare the peaks in A or B, in B, we see this 2-component peak, which tells us that we likely have a primary amine. So students have assigned butylamine to spectra B and N-ethylbutylamine to spectra A. Because spectra B, this 2-component peak, is characteristic of a primary amine such as butylamine. Does this make sense to everyone?
Professor, I'm having trouble trying to see why butylamine is primary.
So looking at nitrogen in butylamine, how many carbon substituents are attached?
Only one.
Yep, exactly.
Okay, that's how you tell.
Yep. Just like when you consider carbons, they're primary, secondary, or tertiary based on the number of substituents. For example, this is a primary carbon. By analogy, this amine would be a primary amine.
Okay.
Further, by extension, N-ethylbutylamine is secondary because it has 2 carbon substituents. Does that make sense?
Yes, I see it now. Thank you.
Perfect. Any other questions on this example? Okay, so let's look at another functional group. So let's look at ketones now. So ketones exhibit a CO stretch that is a very sharp and narrow peak around 1700. Now, a few things to note. Cyclic ketones so if it's in a 6-membered ring, it has a range of around 1715. These are 6-membered ketones and acyclic ketones. 5-membered cyclic ketones have a characteristically high frequency absorbance at 1750. And ketones next to a double bond or aromatic ring exhibit a lower vibrational frequency. So I'd like you to remember that conjugated ketones exhibit a lower vibrational frequency. Does everyone see the difference? Further, if a ketone is conjugated, you will see the carbon-carbon double bond frequencies, right? So you have 2 pieces of evidence if you ever want to claim that you have a conjugated ketone. One, you'd see a slightly lower vibrational frequency for your CO stretch, and you'd see the carbon-carbon double bond frequencies. Does that make sense to everyone?
Yes.
Perfect. So esters, which in this case are like a carboxylic acid with an alkyl group attached to our carboxylic acid oxygen. Esters exhibit generally higher absorbance frequencies of 1735 for saturated esters and 1715 for esters next to an aromatic ring or double bond. So again, conjugated esters exhibit a lower frequency. Does everyone see the difference?
Yeah.
Okay, perfect. So with that in mind, let's take a moment and let's look at the following 3 spectra. I'd like you to tell me if the spectra has a ketone or ester, And is the ketone or ester conjugated or non-conjugated? You may not be able to tell, but I'd like you to use as much evidence as you have been provided to try to assign the identity of each of these compounds. So just remember that esters are generally higher frequency and conjugation leads to a lower observed frequency than usual. So with that in mind, let's take a look at these three spectra. And I'd like you to tell me, from these spectra, do we have a ketone, ester, or neither? And one of these spectra certainly is not like the other, and it almost tells you right away what functionality is present. Does anyone have any thoughts for any of these three spectra? So we have A, B, C. So we have a student noting that in structure B, we have some sort of peak in the 1690 region. So they think that we have a aromatic ring or a double bond. I'm not so sure about the aromatic ring because we're missing these minor peaks, but the carbon-carbon double bond, that's a good catch. We see an absorbance at around 1700, okay? And if we compare our three peaks, we notice that structure A exhibits, and we can observe the highest frequency, CO stretch. So we have students debating and looking. Which structure are you referring to in the chat? Could you clarify? Oh, so you said A. So one student thinks A is an ester because we observe a high frequency, CO stretch, at approximately 1700. That seems reasonable. That looks very much in the ester range. What other piece of data can we figure out from A? Looking at A, is it just a normal ester or is it conjugated? What can we tell about this ester? We see a CC double bond peak, yep, because if we look in the 3000 region, we see a peak in the 3100 region, which corresponds to a carbon-carbon double bond. Yep. So in this case, it's likely that we have a conjugated ester or a conjugated 5-membered cyclic ketone. These would be two viable options that would match this descriptor. Does our assignment for A make sense? Does everyone see how we broke down our peak assignments for A?
I'm a little confused on A only because I saw the highest one looked like it was 1750, so I assumed it was a ketone, but I'm probably missing something else that I didn't see.
Looking at 1750, let's go back to the graph. So 1735, so 1750, the assignment of a cyclic ketone. Looking at this, it's a little bit hard to tell on the onset and differentiate between a typical ester and the ketone. Looking at this, if we consider and we compare a conjugated ester versus a cyclic ketone, and we compare their two frequencies, so for a conjugated ester, it's around 1715 Compared to a cyclic ketone, even when conjugated, it would still be a greater overall absorbance frequencies. So you are correct in noting that if we had to pick the two between a conjugated ester or a cyclic ketone, we would likely conclude that we have a cyclic ketone that's likely conjugated. So a cyclic ketone is a perfectly reasonable assignment for this structure. Yep. And the conclusion that we drew is that since we have such a large absorbance frequency for our CO stretch, it's likely that we have a cyclic ketone at play, or in a 5-membered ring in particular, versus an ester, although it would be pretty close and it's slightly hard to tell. The main deal breaker here is that when you have a conjugated ester, something like this, then our vibrational frequency is around 1710, which is a little low for our observed frequency. Yes, so your argument that we have a cyclic conjugated ketone is perfectly reasonable, and in fact, best fits the data that we have.
Okay, got it. Thank you.
Does that discussion make sense to everyone? How we went through with our options, we compared the spectra, and then we made our final assignment? So in this case, we likely have a cyclic 5-membered ring conjugated ketone. Does that make sense to everyone? Let's look at B and C now, and let's keep working through B and C, and let's see what we can figure out. So, does anyone have any ideas for B and C? I'm surprised no one has commented yet on C, as it has probably one of the most obnoxious, easily identified functional groups in IR spectroscopy. So we have an OH peak, and not just any OH peak. What is this? What is this functionality? A large OH peak. And it almost reminds us of a carboxylic acid. I mean, you do see, well, it's hard to tell if you have a carboxylic acid or alcohol, because if you look in the 1700 region, you don't see much. So it looks like we have an alcohol. So none of the above for C. Does that argument make sense to everyone?
Yes.
Okay, what about structure B? What do we think? What do we think? So we see the presence of a carbon-carbon double bond, and our peak is around 1700. What does that tell us? What does that give us a hint that we have?
Would it be a ketone?
Yep. And is it cyclic or acyclic?
Acyclic?
Yep.
Oh, sorry. Oh, yeah. Okay.
And then is it conjugated or non-conjugated? If we have a carbon-carbon double bond, what do we think?
Conjugated?
Yep. So a conjugated ketone would be a perfectly reasonable explanation. In terms of conjugated ketone versus conjugated ester, it is very close. So oftentimes you'll need another piece of information to tell a conjugated ketone versus an ester apart. The fact that our absorbance is so low likely suggests that it's a conjugated ketone. You should be able to identify whether or not you have a double bond based on the presence or absence of peaks in the 1660 and in the 3100 region.
Professor, I have a question about letter B.
Yep.
So since the largest peak is 1690, and then the other peaks, what I would assume would be like a 17, 15 or 30 aren't big enough.
To say that the largest peak is going to be our CO stretch. And
Okay.
probably the other peak would be the CC stretch. They're in a very similar region. So when thinking about it, your highest intensity peak is more likely to be the CO stretch. So just flipping our assignments around, it looks like our CO stretch, which is the most intense peak, is around 1690, which further leads us to think maybe we have a ketone that's conjugated rather than an ester, because an ester is 1700 at the minimum. Does that make sense?
Yes.
Perfect.
Professor,
Yes, please go ahead.
Professor,
Mhm.
can you please, I see how it could be conjugated, but can you please show me where the sp to CH bond is?
Yeah. So if we draw a dividing line up from 3000, we see this lump of peaks, and that could be the sp2ch, one of those peaks past 3000. If we only have sp3 carbons, you would not see anything past the 3000 line. Does that make sense?
Yes, thank you. Because I was thinking of like, where's the double CH bond? There you
The
go.
CC double bond, it's probably in the 1700 region. So do you notice how there's a large peak and then two small peaks next to it? Do you see that?
Yes.
So these side peaks, one of these side peaks may be our carbon-carbon.
Yes.
When the peaks are right on top
Okay,
of each
thank you
other,
so
you
much.
can sometimes see these major minor patterns. Does that make sense?
That totally makes sense. Thank you.
Perfect. So let's look at the following example, and I'd like you to tell me which of the following compounds contains a conjugated ketone or ester. So I'm asking you to compare these two spectra, and I'd like you to tell me which one has conjugation. Which one has a conjugated ketone or ester? A or B. Only one of these structures is conjugated, and I'd like you to explain why. So looking at the 3000 line, so we see peaks with an absorbance of greater than 3000. That tells us we have an sp2ch, and that indicates the presence of a double bond. What other piece of evidence do we have? What other piece of evidence do we have? If we compare our CO stretches, we see that in A, we have a lower CO stretch frequency. What's also our super definitive piece of proof? If we have a conjugated system, what other signal do we see that indicates the presence of a carbon-carbon double bond? What other signal do we see that's super indicative? If we have a carbon-carbon double bond, what other signal is that should we point out? What other signal tells us that we have a double bond?
The peak to the right of the CO peak.
Yep. And that peak corresponds to what?
To a CC double bond.
Yep. It's the CC stretch at approximately 1680. Yep. So structure A contains our conjugated ketone or ester. And given the frequency, it's likely a conjugated ketone. Does that make sense? Okay, perfect. So let's talk about the last set of functional groups, just as review. Nitriles and alkynes. So nitriles, to our carbon-nitrogen double bonded motif, have absorbances from 2200 to 2300, while alkynes have absorbances in 2100 to 2200. This is a very discrete and unique region, and you don't really see much else in this region. Any question on alkynes and nitriles? Well, that's it for our overview of infrared spectroscopy. We're next, in later class sessions, we're going to talk about NMR, nuclear magnetic resonance spectroscopy, and then we're going to apply each of these spectroscopic methods together to definitively assign the structure of an unknown molecule. So this is one other tool that we've added, and infrared spectroscopy is used a lot in the laboratories. So you need to be familiar with analyzing and assigning peaks to effectively write your lab reports. So that's all I have planned for today's session. So I'll stop the recording.